Margot Gerritsen is a professor at Stanford University and co-founder and co-director of WIDS Worldwide and has expertise in computational mathematics. Margot received her MS from TU Delft and her PhD from Stanford. She and Laura will be online to answer questions during her workshop, What Would We Do Without Linear Algebra, Part 2, diving deeper into the singular value decomposition. All right, take it away.
No, thank you very much. I hope you can all hear me. So I'm Margot, and as Cerise was saying, and I'm here today with the wonderful Laura Lyman, who is also a panelist. And Laura is a PhD student in computational mathematics at Stanford University, and she will be looking at the chat while this workshop is going on and answering any questions while I'm talking. So that's a nice division of duty. Now, Laura also created a wonderful demo, and I'm very excited to show that to you later at the end of this workshop. Now, before we dive in and do linear algebra, let me just tell you a little bit more about the series of workshops on linear algebra for data science that we've put together. So I'm just going to quickly share my screen for that. So I started this with workshop 1 at the annual conference, the WIDS conference in March. And the topic for that workshop was searching and ranking. Now that workshop is available online, so you can find that easily by going to the WIDS website. And maybe Cerise or Valerie can put a link in the chat for you so you can look it up. Now, I looked at searching and ranking, two really important concepts in data science, because to understand searching and ranking, we really need to introduce algebra for vectors and matrices. So in this workshop, we looked at vector multiplication, meaning the inner product. We looked at matrices and matrix vector multiplication. We looked at angles between vectors. We looked at matrices as operators, which is going to be important for today as well. And at the end of that workshop, I introduced very quickly the singular value decomposition. And that's a really, really important concept, not just in data science, but in many areas of science and engineering. And I said at that workshop, said, well, one day we're going to take a little bit of a deeper dive and talk more about it. Well, that day has come, so that's what we're going to do today. Today is all about how the singular value decomposition can really be interpreted and what probably motivated people to look at this. Then in the next workshop, about a month from now, we'll look at the connection between principal component analysis and the singular value decomposition. So that would be fun. That would be next month. And then a couple of months from now, in the last linear algebra workshop for 2021, we'll probably do more in 2022, we'll look at how the singular value decomposition is actually computed in commercial codes. That is a much more advanced workshop. Today, I'm not going to assume much prior knowledge. I'm really just going to assume that you master the concept that we talked about in workshop one reasonably well. Okay, now, for those of you who've taken a workshop from me before, you know that I'm a little bit of a pen and paper person. So I'm actually going to be using my document camera quite a bit today. So I'm going to put my glasses on, and hopefully you will have a pen and paper and you can follow me along. Okay, so now my screen has changed into this document camera, so hopefully you can see everything just fine. Now, first of all, of course, let me remind you what a singular value decomposition is, and also why we're spending a little bit more time on that in women in data science. You know, why is that important for data science? Now, one of the miraculous things in linear algebra is that any matrix, and it doesn't matter what size, whether small or big or rectangular or square, can be expressed as a product of three special matrices: U, sigma, and V transpose. That is the singular value decomposition. Now, these U and V matrices are special because they're orthogonal. And today we're going to look a little bit closer at what that means, orthogonality, and why orthogonal matrices are attractive. The sigma matrix is really quite unique because that sigma matrix is a diagonal matrix. And on the diagonal are the so-called singular values. So sigma 1 through to all the way down to sigma n here. And these singular values are all positive, and they're all listed along this diagonal in decreasing order. Okay, so sigma 1 would be the largest, and then sigma 2, and so on. Now, that's really quite incredible that every matrix can be decomposed this way. And of course, one of the first questions you may ask yourself is, how did they come up with that? So that's what today is about. And the second question, of course, is why do we care? Now, why is the SVD interesting? There are many reasons for this, and we'll see this in workshops 3 and workshops 4 as well. But one of the main ones really is the fact that the SVD can be used for compression. And that is an example that we looked at in workshop 1. Because if I have a expression like this, A is U sigma V transpose, then what I can see, which we'll look at in much more detail in workshop 3, and then you can also derive this yourself, is that A can also be written as an expansion where every term in this expansion is a sigma times the corresponding column of the matrix U times the corresponding row of the matrix V transpose. Now, because these singular values are written in decreasing order, it could happen that only a couple of those singular values are really large and the rest are small. So for compression, what we can do is just remove all the parts, as I've already done here, all the parts in this expansion that are small. And then what we're left with is just this. And that's, of course, very little storage for this matrix. And it turns out to be a pretty decent compression scheme. Now, this compression scheme was so popular for a while that it was even used to compress photos and videos online. Now they use different algorithms, but it has been used for that in the past. Now, the other reason why the singular value decomposition, once we have it, is so interesting is because these singular values really reveal important information about a matrix A. So, for example, it can reveal the rank of the matrix. Now, that doesn't mean much to us in this series because we haven't really discussed rank before, but we'll do that later on. But for those of you who've worked with that, you know what I mean. Now, also the columns of U and V contain information about the matrix. Sometimes it's a little bit hard to get a good feel for that. So today in the demo, Laura will give you an example that provides a bit of intuition of what these columns of U and V actually reveal about the matrix. All right, so today is all about what inspired this singular value decomposition. And along the way, we're going to be talking about orthogonal matrices. We're going to be talking about matrix inverse and several other concepts, okay? And from time to time, I will just come back here in full face, full frontal, so that you know I'm still awake and I'm still here as well. So let's dive into this. And what we're going to do first and foremost is restrict ourselves to 2 dimensions because I'm a terrible artist. So I cannot draw in more than 2 dimensions. And of course, 2 dimensions is also much easier to write down and play with. Okay. And then later we'll say, hey, everything generalizes to much larger systems. So we're going to spend time in 2D. Now, I'm going to introduce a little matrix in 2D. This is a very simple matrix with elements A, B, C, and D. And what we're going to do with this matrix is we're going to apply it to a vector X. Okay, so we just take some vector X and we're going to hit it with that matrix A. Now, if I do that and I do a matrix vector multiplication that we looked at in the first workshop, these are the expressions that we get for the Z's. Z1 is AX1 plus BX2 and Z2 is CX1 plus DX2. This is a simple system of 2 equations in x1 and x2 as well. So we could find an expression of x1 in terms of the z's and x2 in terms of the z's by sort of flipping or inverting this system around. Now that takes a little bit of algebra, so I've done that for you. But if you do this, then you find this expression. So this is sort of the opposite of this, right? This is z expressed in x and this is x expressed in z. Now we can do this, of course, only if this term here, AD minus BC, is not equal to 0. Now that term is called the determinant of the matrix. And if that's 0, this matrix is singular, which means that we cannot invert it. Okay, so we're now just going to assume that we can, and then later we figure out what happens when we cannot. This expression here for x1 and x2, I can write also as a matrix vector expression, matrix vector system. And I can write x here as this matrix now times z. Now this matrix that gives me x back from z is called the inverse of A. That's very similar to inverses of functions. Okay, so we have this situation. Z is created from x by multiplying x with A, and we can get x back by multiplying z with A inverse. Okay, so x is A inverse z, but z is ax. So x is A inverse ax, right? And that means that A inverse A is the identity, which is one thing that is always true and very well known for a matrix and its inverse. And we're going to be using that a little bit later on. Now here above, you may wonder, why am I doing all of this? Because here we just applied A to one vector. Now we're going to play a game where we take a set of vectors and we're going to apply A to this set and see what the impact of A is on this set. Now, what set are we going to use for that? I'm going to use my favorite set in the whole wide world, and that's the set of vectors with length 1, or the unit circle. So on the unit circle, here I draw 4 vectors, but of course infinitely many. All of these vectors have the property that the magnitude of that vector is equal to 1. And again, from the first workshop, we know that means x1 squared plus x2 squared is 1. So this is the expression for a circle. Now what we're going to do is apply A to every single one of the vectors x in this unit circle, and then see, if we look then at the resulting vectors z, what shape these z's make. Are they still in the circle, or is the circle deformed, and what does that look like? So as I'm going to go through this and show you, think about this. What do you think? And if you have an idea, put it in the chat and Laura can tell you whether or not you are right. Okay, so what shape do you think this unit circle transforms into when we apply A to all the vectors in this unit circle? That is the question. Now, to answer this, what I'm going to do is use these expressions that I found earlier for x1 and x2 in terms of the z's, and plug them into the expression for the circle. Then what comes out will be an expression in the z's, and we'll look at the character of that expression. So to do this, there's a little bit more algebra involved, and I'll spare you the details. So I did that last night. And when you work that all out, this is the expression that you get. Now, you may recognize this as the general expression of an ellipse. And it is an ellipse provided that this last term is not equal to 0, but we assumed it wasn't. That is that little determinant again. So isn't this interesting? If we take a unit circle and take any generic matrix A and apply to it, the unit circle is transformed into an ellipse. Now, I remember when I first saw this in the linear algebra class, I couldn't quite believe it. So how come that every matrix makes a unit circle into some sort of ellipse? So an interesting question now is that I'd like to ask you is, if I'd asked you at the beginning of this workshop, how could you change or transform a unit circle into an ellipse like this? What would you have said? What would you have done? What kind of matrix operations would you have chosen to do that? So I'm going to leave you with that question for a bit. How would you transform a blue unit circle into an ellipse if you didn't know that that could be done by any matrix A? And while you're thinking, I'm going to try something out here because I really like trying this, see if this works. I'm going to play a little bit of music, and that music was composed by my son, so that's kind of fun. Did that work? Did you hear the music? Ah, awesome. Okay, so let me tell you what I would have done. The first thing I would have done in the first step in creating this ellipse is I would have taken the unit circle, and this is a bit of a busy slide, but let me take you through it. And I would have applied a sort of a scaling to it. So I would apply a diagonal matrix to it like this, and we call this sigma. Guess where we're going with this, huh? So this looks just like a matrix with singular values, with two positive values, sigma 1, that's the largest one then, and sigma 2. And applying that to the unit matrix would have, well, depending of course a little bit on what that sigma 2 is like. So let's suppose that sigma 2 is smaller than 1 and sigma 1 is bigger than 1. That would have squashed that unit circle a little bit in the vertical in this direction and extended it in this direction. Now to see why, we simply compute all the z's. So these are sigma times x, and we get this expression right here. So we see, for example, that this first in black unit vector 1, 0, so that's that unit vector here, is stretched out to be sigma 1, 0. The second unit vector 0, 1, this one here, is squashed down to now become this little vector, which is 0, sigma 2. We can also take this expression for z in x or x in z, plug it in to the expression for the unit circle, and we see that we get an expression for an ellipse like this, and that's exactly the ellipse that I have right here. Okay, now interesting also here is that the major axis of this ellipse is really set up by the first column of sigma, and the minor axis is set up by the second column of sigma. Okay, so now I have the shape of the ellipse, but the ellipse is still horizontal. So now I need to rotate it. So to do that, my next step would be to apply a rotation matrix. Okay, so I call this rotation matrix U. Now rotation matrices have this form as we talked about in the previous workshop. And here this is a rotation around an angle theta. So that can take that green ellipse that we had and just rotate it over this angle theta to become the red ellipse that we're after. Now, the principal axis here, of the ellipse, the major axis, is given by sigma 1 u1. And that is the first column of this matrix here, sigma u times sigma. Okay, so u times sigma, we can write this as the first column of u. Let's call it u1, u2 times this sigma 1, 0, 0, sigma 2. And if we work that out, then we just get sigma 1 u1 and sigma 2 u2. And this major axis right here is exactly that first column of this transformation matrix, if you like. Okay, so an ellipse formed by applying a matrix, as we illustrated before, to a unit circle, can also be created by a sequence of two transformations. First, the scaling, sigma, and then a u. And u is this rotation matrix. Now I'm gradually nudging this, as you can see, towards the singular value decomposition, right? The singular value decomposition would be that a matrix can be written as u sigma times v transpose. So now we are already at u sigma. So my question now is, ellipses can be created by these matrices, but can it be created maybe by other types of matrices, by a bigger class of matrices? So that is what we're after right now. We're going to look at if there is a larger class of matrices that can create these kinds of ellipses that we just talked about. But before we can do that, we really need to have a closer look at the rotation matrix, because the rotation matrix is a special matrix. It is a class of orthogonal matrices, and we need to play with that a little bit to understand the next part. Okay, so I'll just go back here to the document camera. So this rotation matrix is, as I said, an example of an orthogonal matrix. Now, what is an orthogonal matrix? An orthogonal matrix is defined as a matrix for which the columns are orthogonal. That is the very first requirement. Now it's very easy to check that the columns of this U are indeed orthogonal. We can do that, for example, by computing the inner product and checking that that is 0. So you can do that really quickly, and I'm sure you can figure this out. The second requirement of an orthogonal matrix is that the columns have length 1. And also in this case, that's really easy to see. Okay, so a rotation matrix is this special type of orthogonal matrix. Now, are all orthogonal matrices rotational? No, absolutely not. There is another set of orthogonal matrices called the reflection matrices that maybe you have worked with before, and this is the general form of that. We won't talk about this anymore. For now, we're just going to assume when we hear orthogonal matrix that really it is a rotational operator. Okay, now we can show all sorts of really interesting things about these orthogonal matrices. And the very first one is that if you have an orthogonal matrix Q, that Q transpose times Q is the identity. What that really tells me is that the inverse of an orthogonal matrix is just its transpose. Okay, because this is a relationship that we've seen before for the inverse of a matrix and the matrix itself. Now we can show that quite fast, not too hard, okay? So we set Q to be this matrix with these two columns, Q1 and Q2. Then this would be QTQ. QT would be the matrix where the rows are the transposed columns, right? Like this, Q1 transpose and Q2 transpose. And if we multiply these two out, then these are the elements of the multiplication that we see. So this first element here is the inner product of Q1 with itself, which is the norm of Q1 squared, which is 1. This one here is the inner product of Q1 with Q2, so is this one, but the Q's are orthogonal to each other because this is an orthogonal matrix, so that is 0, and here this one gives me 1 again. So indeed I see that Q transpose Q is the identity, and that means that the inverse of Q is the transpose. Now, why am I interested in this, and what does this have to do with ellipses and unit circles and so on? Well, that's where we're going next, okay? So here's a question. What happens if we apply such an orthogonal matrix to the unit circle? So what we're going to look at is what is this? You know, if we look at the norm of QX, and let's see if we can find something interesting here. Now, the norm of QX squared is the inner product of QX with itself, as we know from workshop 1. So if we change this around a little bit, then this is the expression we get. We get X transpose QTQ times X. But QTQ, we just proved, is the identity. So that drops out. So this is just X transpose X, which is the norm of X squared, which is 1. So we see that if we apply Q to an X on the unit circle, we stay on the unit circle. Now that is not a surprise, of course, because if we rotate vectors on the unit circle, of course, these vectors rotate, yes, but they stay on the unit circle, and the unit circle itself doesn't change. Now, this gives this idea of answering that question that I asked earlier. So I asked, apart from U sigma, what other matrices can create this ellipse? And the answer is that we can take that U sigma and precede it by an orthogonal operation. So if we do something like this, U sigma Q on the unit circle, the very first thing we would do is to apply Q to all these x's on the unit circle. But we just argued that that doesn't change the unit circle. So after Q, we just have the unit circle again, which is exactly the starting place for what we did earlier. Then we squash it down and stretch it out and rotate it, and we get the ellipse. So we can add that Q here. Okay, and now we have this general class of ellipse creating matrices, if you like. Now, of course, something did happen there with this Q because we were rotating things around. And so we have to be a little bit careful when we say nothing happened. Because when we start applying this stretch operator, right, this sigma, remember that with that sigma, we took this matrix, or we took this unit circle, and we squashed it and stretched it to create an ellipse like this, right? And so what we did there is we took one of these unit vectors, 1, 0, for example, right? And we stretched that out to become the major axis. And we took the other unit vector and we squashed that down to become the minor axis. Now, if I had applied Q before, then of course these unit vectors actually came from another place, right? So suppose that Q was a rotation over this angle right here, then this angle right here, then this vector V1 would actually give me, after this rotation with Q, that starting vector for the next operations in this ellipse creation. So we would have QV1 is equal to 1, 0, okay? And we have another vector here, which is orthogonal to this V1 called V2, that when rotated over that same angle ends up in this other unit vector, which then sets up with the next two operations of sigma and u, the minor axis of this ellipse. So we also have QV2 is equal to 0, 1. Now there is a relationship, of course, between these Q's, right? This Q needs to be kind of special. And in fact, we can express Q in terms of the V's. Now, the way we do this is we put these two vectors together in a matrix, QV1, QV2, as two columns of a matrix like this. This is an operation that we use a lot in linear algebra. Then we pull out the Q. Okay, so we get this expression right here. Now we call this matrix big V. Okay, like this. And we see when we plug in these vectors right here into this expression, that this is nothing else but this matrix here, which is the identity matrix. So I see that the Q and the V's are related because Q times V is the identity matrix. But V is an orthogonal matrix, Q is an orthogonal matrix, and we know that for orthogonal matrices, the transpose of the matrix times the matrix itself gives me the identity. So what does this mean? This means that Q is V transpose. Haha. So have we nudged things to the singular value decomposition? Yes. We said we have ellipse creating operations or matrix operations of this form, Q. But that is the same as U sigma V transpose, which is exactly the formula we had for the singular value decomposition. Now, of course, we haven't now proven that every matrix can be expressed in this form, but what we have shown is that matrices form ellipses, and that for every matrix, we can find another sequence of matrices, U sigma V transpose, which will form that same ellipse. Now, here is an example of that. So I take some matrix, that's this matrix right here, and I actually find that that matrix can be expressed exactly as U sigma V transpose, with this for sigma and these rotation matrices for both U and V transpose. So here's an example where both of these generate the same ellipse, and in fact, they are identical. Now, when people started looking at this and this sort of ellipse generation and realizing that we could break the construction of this ellipse down into those three steps right here, U, sigma, and V transpose, they really got this idea of, oh, maybe we can express all matrices like this. And that is how the SVD was really born. So what have we seen? All matrices transform a unit circle into an ellipse. Matrices like this do this also. And so the logical question is, can all matrices in fact be expressed like that? And the answer is yes. Now, thankfully, we are not asked to actually prove this. So the proof that this is true is a little bit complex, but now you have some intuition of where this comes from. Okay, so we have just a little bit of time left, and I want to quickly discuss what happens when we actually have a matrix that is singular. So we talked about that not all matrices are invertible. Let me go back here to this document camera. Okay, so not all matrices are invertible, and we already said that we probably have a problem when this expression here, which is called the determinant of a matrix, when that is 0. Now here's an example of a matrix that's absolutely not invertible. If I look at AX, I get this expression, and I see that X2 doesn't matter at all in this expression. So to create Z, I can create the same Z with many, many different X's. So that means I can never retrieve X back from Z. There's not a one-way street there, right? Many, many different X's give me the Z. So this matrix is not invertible. Here is another example of a matrix that is not invertible, or a singular matrix. In both of these cases, by the way, we can easily check that the determinant is equal to 0. And that's a matrix like this. We see that the columns are dependent on each other. One is just 2 times the other, and so are the rows. So if I now look at AX, I see that the first element of AX is x1 plus 2x2, and the next element is twice that. So if that is Z1 and Z2, then how can I get back from this? Because really these are 2 similar equations. And to solve for x1 and x2 as a function of the z's, I would need 2 unique equations in x1 and x2, and I really only have 1. So that's also a singular matrix. But never mind, I did say to you earlier on, and that is what we postulate, that all matrices have a singular value decomposition, so also a singular A. So even those matrices before can be expressed this way. Now, the interesting question, of course, can we say anything about this singular values if we have a singular matrix? Now, one way to get intuition is exactly through this ellipse story that we just had. So if we went back to the ellipse and ignored the fact that we used this ellipse construction because we assumed that we were invertible, then this is the expression, the general expression we got for the ellipse. But now AD minus BC is equal to 0. So this drops out. And in fact, when AD minus BC is 0, this whole expression for the ellipse sort of collapses. So after a lot of algebra using that expression, AD minus BC is 0, we actually find that the ellipse just changes or collapses onto a line. So if I had a non-singular matrix, I could create lovely ellipses like this, with a minor axis set up by sigma 2, right? So this would be sigma 2 U2, and the major axis set up by sigma 1 U1. But now in this case, all I get is a line. So this ellipse seems to collapse. And that means that the sigma 2, at least the sigma 2, should be 0. There is no width to this ellipse. It just collapses onto a line. So what we see is that if we have a singular matrix, the singular value of that matrix is in fact 0. Okay, so that's interesting. So if we looked at a matrix like that, right, and we expanded it in singular value decomposition, this is what it would look like with a 0 for the sigma 2. Now, if we multiply these 2 matrices out, then that means that we get a 0 vector right here. And what that really means is that U2 just doesn't play a role. So when we look at U, the only important part there really is that U1. The only important part here is the sigma 1. And when you look at this matrix vector multiplication, you can also see that V2 actually doesn't play a role at all either. Because it doesn't come up. It's always multiplied by 0. So the only parts that are important are U1, sigma 1, and V1. And we may as well, therefore, write this matrix or the singular value decomposition in compact form. And I put this down because Laura will be using that in the demo going on. Now, one of the things that we've seen is that the singular values of a matrix give us information about whether or not the matrix is singular. And if we expand this now to bigger matrices, that generalizes to giving us information about the rank of a matrix. And in workshop 3, we'll really spend some time on that. But before we look at this wonderful demo that Laura generated to give you a sense of what the singular value decomposition can tell us, we really need to look at a bigger matrix because she is going to use a bigger matrix. Now, if we have a singular value decomposition that is much larger, so for example, we have an n by n matrix A, and in that matrix are a bunch of, or this matrix has a bunch of 0 singular values, then the singular value decomposition could be written like this. And again, everything that is connected to the 0 singular values really is not important. So only the first R non-zero singular values are important, the corresponding first R columns of U, and the corresponding first R rows of V. So again, for a matrix like this, we can write it in compact form, and that is what you will see Laura do. Okay. So what we've done today in this workshop is look at sort of where the singular value decomposition comes from. And we did this by staring a lot at unit circles and ellipses. And along the way, we looked at orthogonal matrices and we looked at inverses of matrices, and give you just a little bit more intuition in what this singular value decomposition can do for us. But we'll get a bit more intuition by looking at this demo. So I'm going to stop soon, and then we're going to play this demo, which Laura taped for us. And I just wanted to say thank you for joining me at this really early hour. I hope you're still awake. I hope you learned a little bit about linear algebra, and I hope you're going to join me for workshop 3, and Laura as well, because I think Laura will stay involved with that workshop too. So Cerise, it's over to you to play the video.
In this example, we will use the singular value decomposition to examine the underlying structure of some movie data. Let A be a rectangular data matrix whose rows correspond to users, columns to movie titles, and entries to movie ratings. Specifically, we're going to let A sub ij denote the rating that user I gives movie j, assuming such a user saw that movie, of course. For instance, here we see that A sub 3.2 indicates that user 3 saw movie 2, which in this case is Alien, and gave it a rating of 1. In this model, A sub ij equals 0 if and only if user I has not rated movie j. Namely, we're not allowing users to give ratings of 0. Right away, we can see a block structure in the data matrix A. Namely, the sci-fi watchers are only reviewing the sci-fi movies, and the romance lovers are only rating the romance films. This means that our data is stratified by these 2 categories overall, in this case, movie genres. Now we can see this structure in the data matrix A based on how we chose our users and movies in terms of the ordering in this matrix. But in real life, of course, it's going to be more complicated. Given these complications, the SVD can be used as a tool to glean information from an otherwise messy dataset. In particular, we're going to see how in this toy example, the overall categories, or movie genres, are reflected in the SVD. The first singular value is larger in magnitude than the second singular value. This interpretation is that the first category, in this case sci-fi, has relatively more influence over the movie data overall than does its counterpart, romance. This makes sense because here the sci-fi movies are rated higher on average, and we can note that 4 users are watching sci-fi, while only 3 are watching romance. So not only does sigma tell us how many categories there are, but it indicates their relative strength or influence when characterizing the data. To see this, suppose I change user 3's ratings from 1s to 4s. As a result, the first singular value would increase, and the second one would remain unchanged. Similarly, if we update user 5 to give his ratings of 2 to sci-fi rather than romance, we would again see sigma sub 1, 1 increase. However, we would also see in this case the second singular value decreasing, since romance has effectively become a less important category from losing a user. Heuristically, we can think of U as a user-to-category similarity matrix. U encodes the row information. In this case, it asks, how much does each user belong to a given category? Or namely, how strongly does a user prefer a particular movie genre? You can see that among the first 4 users, user 4 has the largest corresponding entry, meaning she has the strongest preference for sci-fi among her compatriots. We can see something similar for user 6 in romance movies. The matrix V is the so-called categoried movie similarity matrix, or how well each movie fits into the categories sci-fi and romance. Within each cluster, you can see that every movie matches its genre to the same extent, since all of the users give uniform ratings. For instance, we can see that user 1 only gave ratings of 1, the second user only gave ratings of 2, etc. Now, suppose we diversify within a cluster. Consider the second user. Let's call him Pete. Suppose he likes Alien more than he does the other two sci-fi movies. Now, U and V get additional columns to span the extra dimension introduced by this new rating, since the first 3 columns of A are no longer identical. The additional singular value, 2.11, represents a newly introduced category within the dataset. Broadly, a subset of sci-fi movies that are like Alien. Note that the entries in U, sigma, and V that correspond to romantic movies are unchanged, since we only updated a rating within the first cluster. Up until this point, this example has been rather contrived, in the sense that each user only rates movies within one of the 2 genres. So what if our second user, Pete, watches Amelie and gives it a 4? Consequently, there's going to be filling in from cross-pollination, so to speak, where there were previously zeros. As before, there's a new singular value to represent the new category introduced by Pete's updated rate. Only now, this category could reasonably be described as a romance sci-fi hybrid or connection. The takeaway is this: both the third singular value and the magnitude of the fill-in correspond to the strength of this connection. What do I mean by that? Well, let's say Pete actually gave Amelie a smaller rating, a 2 instead of the 4. Then the corresponding third singular value would be smaller, and the fill-in entries would be smaller in magnitude as well. Even as the data matrix becomes more complicated, the changes will always be reflected in the SVD. Accordingly, the SVD can help us better understand some of the key characteristics of the information given to us.